Now we found a formula for the first order correction of the eigen energy, E1, if you like. It was, well, it's in the previous session that you can't see it, but it was bra U0, and then between two vertical lines the H hat dashed, in other words the perturbing Hamiltonian, and in the ket was another U0, well, UN naught. So in other words, that to the nth eigenenergy, the correction, so En1, first order correction to the nth eigenvalue, it's an expectation value, right? It's where the wave function that you're talking about is the nth eigenstate of the unperturbed system, right? It's you can look on it as, because that's the formula, the bra operator ket, where the bra and the ket eigenfunctions are the same. That's the formula for an expectation value. So you can look on E1 as as the expectation value, the average measured value, same thing, of H dashed, right? Where the eigenfunctions in the bra and the ket are of this form, the unperturbed eigenfunctions. Okay, so we've found a formula now for E1, or En1, the first order corrections to the eigen energies. All right, how about the eigenfunctions? How about UN1, first order corrections to the eigenfunctions, because we've done it for the eigenenergies. Well, we can do that also fairly readily from the equation plus circle, which you can't see. It'd be nice if I could just move the camera so easily, but I can't. It's set up rigidly, to get the exact camera angle so it fits in the image. I can't just easily modify it. So you really do need the textbook as well. Anyway, so you'll need to look at the previous session for this equation, and just either go back and look, or write it out on paper from the previous session and then use it here. But we can now find the first order correction to the eigenfunctions in a similar way as we did just before with first order corrections to the eigenenergies, right, the eigenvalues. So what you do is, so you go to this equation, plus circle from the previous session, you multiply on the left of both sides by now, not n, m, okay, and integrate. So almost the same as we did before. The one critical difference, of course, is now it's m here, it's not n. So I ask you to do this for homework. Now, in the case where n and m are different, n does not equal m, you'll end up getting this. So it's not difficult. So do that for homework. So multiply on the left both sides by this and integrate, and you'll end up getting this expression. Now, so what? Why is this interesting? Well, look, you've got a term here. You've got an expression for these coefficients, these A and M. Now, from the previous, was it the previous one session? Yes. Now, remember we expanded the first order correction to the eigenfunctions, U1 or UN1, as a weighted sum of the eigenfunctions of the unperturbed Hamiltonian. In other words, the UN 0. Okay? And the coefficients of those UN zeros were these. Okay? Well, we now have a formula for these. So in other words, we now know the first order corrected eigenfunctions. In other words, UN1, right? Because we know this. And we know this because we can calculate this. Now these are the zeroth eigenenergies, right? The n and m. So we know these. We can calculate this, right? Now this case, this is the full big N squared matrix. Before I was saying we only needed the diagonal terms n, but in this case we need the full matrix n, h dashed. Okay, so we can calculate that. We know this, so we can calculate the whole thing, and then hence we know the coefficients a and m, and if we know these, we can plug these values into the expansion of UN1, the first order correction to the eigenfunctions. So these become then, this becomes the coefficients of the first order correction to the eigenfunctions from previous, the weighted sum. So UN1 equals sigma a and m um 0. Okay, so we now have we now have calculated the first order corrections to the eigenfunctions. Okay, so we now know UN1. Now this is the case when n is not equal to m. Now what about, got one left over, one case left over. What happens when n and m are equal? Well, you can normalize the UN, and you'll find it's purely imaginary number, and you can make it disappear by multiplying it by an unobservable phase. Now, that didn't seem to me obvious. It's an introductory course, right? So this is another bit of an iceberg.